Hello, I'm Jess Garcia. I am the founder of Wani Security, a global detection and response firm. And I'm also a SANS instructor, a senior instructor with the SANS Institute. Okay, I'm very happy today to be here talking about artificial intelligence applied to DFIR, specifically to threat hunting and digital investigations. Okay, I will start by talking about the DFIR myth. In DFIR, we have this red button myth in which in a distant future, we will have the capability to actually press a red button and have our investigation solved automatically. I'm sad to say that artificial intelligence is not there yet. I don't think it's going to be there anytime soon. But the point of this presentation is actually showing you that even when we are not there, and we will not be there soon, artificial intelligence and machine learning, deep learning can be a very powerful weapon in digital forensic science response. Okay, so this talk was about turning AI into a powerful weapon. Now, our objective is to help forensicators, digital forensic experts, to move from or to complement their already existing capabilities with their powerful commercial or open source tools or platforms, into including other newer technologies such as big data, most interestingly, data science and artificial intelligence. Last year, I started a project called Data Science Forensics. Okay, you can go to the datascienceforensics.io website and you will find all about it. It's a free project, it's a community project, and we've been doing quite a few things during the last year. The road so far for the supernatural founds out there has been several sub-projects that we've been creating, such as the Data Science Forensics Library, which is a project that facilitates the ingestion and analysis of forensic data from the output of your tools to your data science environment, typically Jupyter, for those who are familiar with that. We've also been working on a virtual machine that facilitates all this. Okay, setting up a a data science environment with Jupyter and all the plugins can be a little cumbersome. So we are working on a virtual machine, a DAISY, which is designed for data science, artificial intelligence applied to DFIR. We've also been working in defining a model, HAM, the Harmonized Artifact Model, and some other formats, which facilitate the harmonization of all the tool outputs into a format which is digestible by data science and artificial intelligence programs. Another very cool project we've been working on is ADAM, the adversary emulator, specifically for data science, as I will introduce later, and to end up with the start today, V4ML, which basically is machine learning for DFIR. Okay, so last year at the SANS DFIR Summit in July, I presented a little bit of an appetizer of this project, okay, the first steps, and I was able to present how a specific a specific machine learning model called autoencoders are very good at detecting anomalies, in that specific case about malicious logons. Okay, if you want to see the whole presentation, you can go, you have the link in the bottom. So that was the first step. But during this year, from July till now, we've been digging deeper. Okay, so we know that machine learning cannot catch evil activity because evil is something blurry in any case, right? But let's focus on what machine learning is good at and what technologies it can provide, okay? So we know that machine learning, when you provide a specific data set, is good at understanding the big picture in that data set scope. It's good in complex scenarios with many variables and in a very specific field, okay? So if you fulfill those let's say restrictions, data science will be doing a good job. Machine learning will be doing a good job, okay? And specifically, what type of things can technically machine learning do? Well, I'm not going to be going into the technical detail, but it can do classification, clustering, prediction, noise filtering, and more interestingly for us, anomaly detection. In the end, a malicious event tends to be an anomaly in many cases, okay, from different points of view that I will be explaining a little later. So we're going to be using anomaly detection in different areas, threat hunting, digital investigations, and possibly in the future CTI and other different areas. So what is our objective? Well, our methodology is going to be the first part is going to be the traditional DFIR process, where you have some data, what you collect from your computers, from your different environments, you process it, and you get some output. From there, we will ingest that into our data science environment, transform it to have a common harmonized format that is let's say, friendly for the data science environment and more interesting in this case for the machine learning environment. And once we have that, we will try to detect anomalies in that data set. Okay, so in order to make this much more interesting, what we will do is ask ourselves a big question. Could we be able to detect an unknown attack without indicators of compromise, just by doing multi-artifact machine learning anomaly analysis? And to make it even more fun, we will apply to a very specific case all of you know about, which is SolarWinds. So would we have been able to detect the SolarWinds attack with a methodology like the one we are going to be presenting if we were doing threat hunting back in the time the way we are going to be discussing today? We'll answer this question throughout the presentation, okay? So what we're going to be presenting is a methodology which is divided in 3 layers, as you can see here. The first layer is the traditional threat hunting, a digital investigation layer, where you're going to be hunting for some threats, and then you're going to be getting some data, some output from your forensic tools that you're going to be analyzing. The second part, which is the second layer, the yellow layer, is going to be machine learning. We're going to be defining a machine learning model which is able to detect those things we want to detect. And the third layer is taking that to the real world. Okay, now that we have a machine learning model that works, can we actually apply that to real world data and make it work? And let's go for it. Okay, so we're going to be starting with the DFIR layer. In the DFIR layer is the traditional threat hunting model. We're going to be defining a threat hunting model in which we're going to be using the MITRE ATT&CK framework, and we're going to be using, for example, let's say a policy where we're going to be hunting for the top 5 most common adversary techniques. Okay, we can use the Red Canary threat detection report, and if you take a look at that report, it says that the most common adversary techniques used by adversaries are process injection, scheduled tasks, Windows admin shares, PowerShell, and remote file copy. Okay, so let's imagine that that's our policy and we're going to be hunting for that. Guess what? SolarWinds actually uses T1053005, which is basically Red Canary Top 2, which is the creation of malicious scheduled tasks. Okay, so this means that if we were hunting for scheduled tasks and the scheduled tasks were up in our analysis scale, okay, the malicious scheduled task, we could have been detecting the SolarWinds attack. First off, what we're going to be trying to do is get familiar with this T1053005 technique, okay? If you want to know how, from the offensive point of view, how it works, okay, how the creation of scheduled tasks, malicious scheduled tasks works, the Mordor project by Roberto Rodriguez and his brother basically is a great location to look. What they've done is an amazing work in terms of profiling how different types of techniques, of MITRE ATT&CK techniques, are actually implemented and showing you how they work. Okay. A complementary project to the Mordor project is the Threat Hunter Playbook, also by Roberto Rodriguez, which actually defines how to detect those attacks, mostly by using detection on event logs. Cool. So if we look at this, we could be able to know how to detect the creation of scheduled tasks using event logs. But of course, we are forensicators and we want to have a wider view. Okay. And this means that we are not going to be restricting ourselves only to event logs, but we are going to be also covering forensic artifacts. For that, what we can do is rely on the SANS DFIR Hunt Evil poster. The SANS Hunt Evil poster is a fantastic resource for identifying different types of techniques from the forensic point of view. And as you can see in the slide, specifically for scheduled tasks in the destination machine, you can see that there are 3 types of artifacts that are typically created: event logs, registry, and file system artifacts. In the event logs side, you have the security event logs, and more specifically, the scheduled tasks event logs. In the registry, you have different entries. And in the file system, we're going to be focusing on a very specific directory, which is the Windows System 32 tasks folder, which is where the files are created when you create scheduled tasks. Okay? So in a nutshell, we have defined what we want to detect and how we're going to be detecting it. Okay? At this point, what we're going to be needing to do is collect the data, right? And that's the traditional forensic processes. I'm going to be using my CN or my EDR or forensic agents to collect the artifacts. Then I will process them as needed with other tools, potentially like CAPE or Eric Zimmerman tools or Plaso, Volatility, or what have you. And it will eventually generate a number of files in different formats, typically JSON or CSV. Cool. So at this point, we have finished the DFIR process without analysis, but with the output of our forensic tools. What next? We're going to be focusing now on the machine learning part of the scene, which is the most interesting, obviously. Okay. Once we have the output of this tool, what you can see in the slide as raw output, what you have is the data, the output of your forensic tools in typically a JSON or CSV format. Okay. However, if you use different tools are going to be having different naming conventions for different columns, and that's going to be a mess. So what we need to do is harmonize that model in what we call the HAM model. The data science forensics library that I was talking about helps in harmonizing that for different tools like Kansa, CAPE, Volatility, and some others. From there, we will apply the machine learning process of feature selection and feature engineering to get what we call the HML format, which could be the features that are useful for that specific type of detection from the machine learning model point of view. Then we go now to explaining you what model. I've been talking already about the autoencoder, but what is an autoencoder and how it works? How does it work? Well, the thing is the following. What you're going to be doing is presenting a number of data entries to this model, to this autoencoder. We're going to be going high level, and we're going to be imagining we are trying to detect cats, anomalies in cats, okay? So what we're going to be doing is presenting many different cats, and the machine learning model will get the essence of what a cat is, what you can see in the middle. This is by doing a process of dimensionality reduction, but removes all the non-important stuff and retains the essence of what you're looking for. And then what it will try to do is, with that essence, try to reconstruct the original cat. So if it's a very normal cat, the essence of the cat will be very well defined, and you will be able to reconstruct the cat. But if it's not a cat, you will not be able to reconstruct the cat properly, and that will create a huge error. The measure of that error, that you will be seeing in a couple of slides, will tell you if we are good, if it's a cat or if it's not a cat, okay? So how does this map to the discussion we're having? Here, what we have, let's think about the task scheduled task event logs, okay, and the specific events. That's what we're going to be providing. Each of the columns, each of the fields of those event logs is what we're going to be providing to the machine learning model, okay, to the autoencoder. And then, as you can see in the slide, we're going to be providing the event ID, the computer name, etc., for many computers, okay? So after seeing this, it will know what the essence of scheduled tasks logs look like, and it will be able to identify what is not the same as the rest. Okay, note that this is unsupervised. At no point there is a human saying this is a cat or this is not a cat. What the model will do is like This is very different from what I know that a cat is. You need to evaluate if this is a cat or not a cat, but it will give you the measure of the anomaly. And this is where we go to precisely the measure of the anomaly, what we call the loss in machine learning. Okay, with a standard autoencoder, if you present normal cats, you will see that the error is very low, like you see in the bottom of the screen. Okay, the normal cats. If you present cats which are still cats but weird cats, okay, it will give you a higher error, which are the cats that you're seeing at the middle of the screen. And if you provide to the neural network an elephant, it will say, oh my God, the reconstruction error is huge because I cannot reconstruct an elephant with the essence of a cat. Okay, so by knowing how big is the loss, the error, we can know if that is an anomaly or not. Okay, we've been doing a research further on autoencoders. There is a type of autoencoder which is extremely interesting. It's called LSTM. LSTM autoencoders are actually long, short-term memory autoencoders. Are autoencoders that have memory. They remember the past. So it's not only now if the cat is strange or not. It will also take into account when the cat appears. So if I have a normal cat, which is a completely normal cat, but that cat never appears at 2 a.m. and all of a sudden I see the cat appearing at 2 a.m. in the morning, the LSTM autoencoder will say, hey, I have an anomaly here. This is an anomaly not because it's a cat, a strange cat, because it's a cat that is appearing at a time that is not supposed to. Okay, so basically it can detect an anomaly taking the time into account. Cool. So we have selected two models, the standard autoencoder and the LSTM autoencoder. And the next thing we're going to be doing is injecting the malicious, let's say, attack in our data. Okay, since we normally don't have the SolarWinds attack in our networks, we will have to emulate it. And for that, we will use Adam. Okay, Adam will emulate the attack by injecting the malicious attack following, well, the indications you provide in the data that is going to be ingested by the machine learning model. And then we will see if the machine learning model is able to catch detection or not by evaluating the anomalies that it has produced. Okay, so fantastic. Let's say we are happy. We have identified that this autoencoder and autoencoder LSTM are good at detecting this type of technique. Okay, and we have fine-tuned certain parameters to make it effective. So what would we do at that point? What we would do could be to go to the real world. Okay, now we have this function, which is, as you will see later, is find machine learning anomalies. Okay, and you will provide the data, the real world data, and you will figure out you will apply the machine learning models and figure out what anomalies are shown. If you have multiple artifacts, you can follow the traditional digital investigation process of analyzing one thing, and then from the findings you find a filter other type of evidence, and then analyze that and filter and pivot to another artifact, and so on and so forth. You could use the CTI platform, okay, in case there are IOCs, but remember, in this game today, we're not going to be counting with, we're going to be assuming there are no IOCs, so we will leave behind the CTI platform. We will just focus on the manual analysis. So this is, in the end, what we could do. So we could actually analyze the event logs for the scheduled tasks, then select the top 25% anomalies, for instance. You will decide that percentage based on your analysis on the machine learning phase. Then you extract those and filter the file list. For instance, you can generate a file listing with MapTime or other tools, okay, Analyze MFT, etc. And then you can filter those files which have been presented as anomalies in the event logs, and so on and so forth. You could pivot to other forensic artifacts as you do in the real world, okay? And to end up with, you could analyze, your analyst could analyze what is found, what are the top anomalies, and then dig deeper on those. So demo time, guys. What we're going to be doing now is identifying if this works in real world data. What we're going to be presenting is we're going to be restricting our analysis to only 2 artifacts. I think it's enough to show how this works, and it's not going to be complicating things too much. Okay, those 2 artifacts are going to be the event logs, specifically the scheduler task event logs, and the file listing. File listing means not the contents of the files, but the metadata of the files for the files in the Windows System32 tasks folder, which are where the tasks files are created when you create a scheduled task. Okay. This is going to be, I want you to know that this is real world data. This is not fake data. We have been partnering with a customer of ours in order to do these demos, Fortune 500 global company. They provided several months of data. We have selected 30 days of data, okay, from 100 production servers, okay. That accounts, those 30 days of data accounts for 220,000 events, more or less, for the schedule tasks event log exclusively, and about 24 million lines in the file system timelines. Okay, so quite a lot of data. Again, totally real world data, production servers. So the next thing we've done is we've processed this forensically, as I've shown you in previous slides, and we have injected the SolarWinds attack. What we've done is gone to the sources, the intelligence sources that explain you what the SolarWinds attack actually looks like from the point of view of the scheduled tasks creation. And then what we've injected is the scheduled task in 2 locations, in the event log data and in the file listing data. Okay, and what we are going to be deciding or framing is the following. If we count with the possibility from the resource and point of view in my threat hunting team to analyze the top 100 anomalies, okay? So my team will be able to go through all the 100 top anomalies and analyze deeper if they need to identify if it's a false positive or not. We're going to be defining 100. It's going to be depending on your resources if you decide it's 1,000 or only 50, okay? But it doesn't matter. Let's define 100. And the question will be, I will detect the SolarWinds attack if the malicious task is in the top 100 anomalies, because that's the resources I can use, okay? Guys, in order for you to understand very well what I'm going to be doing, I'm going to be dividing the demo in 3 phases, okay? In the first phase, I'm going to be introducing you to the autoencoder. I want you to get a feeling of how an autoencoder actually works, okay? So this has nothing to do, this first part has nothing to do with the SolarWinds attack, okay? It's just to get a feeling, and I will explain some machine learning concepts and such. The second part, we will use the pivoting methodology, okay? So in that, I will explain later exactly what we're going to be doing, but we're going to be pivoting, we're going to be analyzing the event logs, we're going to be analyzing the file listing, and then we're going to be pivoting from the event logs to the file listing, okay? So that's another technique. And the third phase of the demo will cover specifically the use of the LSTM autoencoder that, remember, is able to detect the time variance, okay, or the anomalies in time, and we will try to define, or we will try to identify if that's actually doing the detection, okay? So let's start with getting a nice feeling about this autoencoder. How does it work? Let's learn about it. Let's start with the demo. Here we have a total of 6,000 entries, which will be the whole data set. Don't worry about that. And we have a total of 8,500 unique entries. What I'm going to be doing is I'm going to be running a machine learning function called find anomalies ML, which I have coded, okay? As I say, this is open source. And I will be running this with a simple autoencoder, as you're seeing now on the screen, in order to produce some anomalies. Okay, in the end, it's going to be telling me what are the most anomalies and the less anomalous entries by looking at the error. I have injected a first event which is really strange. I made it up, so it's really strange. And I will run the machine learning for 3 loops. Why 3 loops? Well, it doesn't need to be 3. It can be several loops, but it's important because the machine learning has a degree of randomness, okay? So you may run it one time and not work properly. So as you can see there, the machine learning model, which is based on 3 layers, okay? As I was showing before, is a simplification of the autoencoder. And if you run this, you will detect the event on position number 20. 20, top anomaly out of 8,500. Well, that's a pretty good number, right? So it has detected that it's very anomalous. I'm going to be creating now, I'm going to be running the neural network with a less strange event, okay? This event is more similar to the rest of the events that are seen in those servers, okay? And how in what terms? Well, in the different fields, okay? Username, action name, etc., etc. And if I run the machine learning model again, I will basically detect this as anomaly number 271 out of 8,500, which is still not bad, okay? So if I provide something very anomalous, top 20, if it's not so anomalous, top 200, let's say, or top 300, let's do something which is very average. I'm going to be injecting an event which is very, very similar to the rest of the events that are happening in those servers. And guess what? My detection is 2,000 in terms of anomaly, 2,000 out of 8,500. So obviously, when I feed the neural network something which is very similar to what you've seen, the thing is that you will be you will not be able to detect this as an anomaly because in reality it's not an anomaly. It's very similar to the other events. Okay, great. So now you are familiar on how an autoencoder works. The more strange the input, the bigger the anomaly rate, or the upper it appears in the list of anomalies. The more similar to the rest of the data set, the lower it appears in the anomaly scale, let's say, right? So let's go now to the interesting part. Let's go to the SolarWinds case. The phase number 2, as you may remember, is the pivoting phase. So what I'm going to be doing is 3 things. First, I'm going to be running my machine learning model, the autoencoder, the standard autoencoder, on only the event log data. Then I will be running the simple autoencoder on the file listing data, standalone, okay? And in third place, I will filter the file listing with the anomalies, with the top 25% anomalies of the event log data. So let's say I run the event log data, I get the top 25 most strange things, and then out of the task files, I filter those that appear in the top 25%. Okay, that is useful to eliminate noise that could be created by other things in the file listing data set. Okay, so that pivoting, just like in the real world, is going to be filtering out noise. Okay, the third, so this is going to be what we're going to be seeing now. Okay, let's go for it. Remember, first part, analyzing only the anomalies. Out of the 8,500, I'm going to be looking at the SolarWinds attack. The SolarWinds attack, you're seeing the 4 entries that are associated to Event Cache Manager, which is the name of the scheduled task that is created by SolarWinds. Okay, there are 2 events associated to the creation of the task, and 2 events associated to the execution of the task. And as you can see, the results are not very good. The tasks are not so anomalous. I get a detection of 1,700 out of 8,500. That's not very good. So from my analysis point of view, I would have not detected it. Okay, it's not in my top 100. Let's go to file listing now. I'm going to be analyzing what are the top anomalies, and if this entry, this malicious scheduled task, as you can see, I have inserted it in the file listing data set. You can see the different timestamps, you can see the size of the file, the computer name, etc. I'm going to be running the simple autoencoder, and I'm going to be seeing how strange that SolarWinds file is. And guess what? 1,800. Not very good. So I'm not able to detect as a very big anomaly on the file system on its own. So the third part, as you may remember, I will going to be filtering the file listing with the top 25% anomalies of the event logs. And that gives me a data set which is very reduced, 735. And in that reduced data set, I'm going to be running my machine learning process. Okay, let's see what we get. The detection is top number 91 anomaly. According to the scenario we had originally defined, I have detected that malicious file on the top 100, so my analyst would have investigated it in depth and would have luckily detected this attack. Okay, so well, it looks like as a summary, if I do the analysis of the scheduled task event only, I don't detect anything notable. If I do the analysis only on the file listing, I don't detect anything notable either. But if I pivot, as I could do in a real-world investigation, on the top 25% anomalies, I get a reduced data set, and my hit is now in the top 100, which means I could have detected the SolarWinds attack in my threat hunting process. Fantastic, okay? That's great. So we have methodology. Let's change now to the phase 3 of the demo. In this case, we're going to be using the LSTM autoencoder only for the event logs, okay? So we are not going to be pivoting, we're going to be keeping it simple. Okay, let's see how good does this new LSTM autoencoder technology, okay, in detecting the SolarWinds scheduled tasks event logs. Okay, so remember that we have injected 4 scheduled task event logs, 2 for the creation and 2 for the execution. That's the normal thing. Okay, and what we're going to be doing is running the machine learning process on 30 days of data. As you can see, there are 30 days of data that accounts for approximately 220,000 events, as you're seeing the screen now. And that's a lot of events, right? We're going to be running the machine learning, the LSTM machine learning model. As you can see, it's a little different than the previous one. It's an LSTM learning model. It has other layers that we didn't see before. And since this is a much larger data set, it will take about 15 minutes for the data to get processed and to get the predictions, to identify the anomalies. Okay, I have obviously edited the video, so you don't have to wait 20 minutes here, 15 or 20 minutes. And guess what? Now, what is the detection of the creation of the tasks? The creation of the tasks, which are event logs, event IDs 10X and 140, are detected in the first and second place as the top 2 anomalies in this data set. So individually, these events were not special, but because they appear when they appear, when they don't, that event does not normally appear at that moment in time in the 100 server data set, that is detected as extremely anomalous, as the most anomalous event in that month, okay, of data. So as you can see, it's a pretty interesting result, okay, being able to detect the SolarWinds attack by a standard threat hunting process using machine learning. Okay, so hope you are so excited as I am. In the end, I want to summarize saying that everything is open source. Okay, so you will find this on the DS Forensics website. The DS Forensics library will help you accomplish all this and all the other projects I've been mentioning. This is real world data. We didn't make anything up. We ran, the only thing we did was do the injections in the real data. And well, we are going to be continuing investigating to make this more and more actionable. Okay. Closing remarks. Artificial intelligence is not magic, but as you've seen, it can be an extremely powerful weapon for DFIR. And closing remarks, as you know, how do you apply this when you go back to the office? You can download the DAISY virtual machine, which is going to be ready for analysis. The more memory you can give it to it, the bigger data sets you will be able to process. We've been playing with memories of 256 gigs, 1 terabyte of memory, but if you have 16 gigs of memory, you will still be able to play with it, or 8 gigs, only with the smaller data sets. Go to the DS Forensics website to get familiar with how all these technologies and everything that I have presented works. Define what MITRE attacks techniques you want to hunt for. Identify the artifacts, collect them, process them, feed them to the machine learning model, and analyze the anomalies. Review, pivot, repeat. Okay, so this is all. I hope this can be useful for you. And if we have created a web page under dsforensics.io/RSAC21 to, well, collect all the information in this conference. In general, you can go to the datascienceforensics.io website for all the information about these topics, or to One Security if you need professional help on this area. Okay, thank you very much. And as you know, I'm around for questions. This has been going on long, but and I hope you've been able to send all your questions already. But if you have more, I'm here. Okay, thank you very much, and see you around.